So, chapter 16. Do you have a preference which one to do? 22? Okay.
Chapter 16.
That's what she said. Yeah. I'm not looking at a list. Is that okay? Do you want to double check? Yeah? Do you want me to look? Yeah, here it is. Yep, it's right down there.
Oh, I have it. There it is.
Oh, question. Am I looking at problem instead of question?
So problem 22 from chapter 15.
Gotcha. Okay.
And
Okay. Gotcha. All right. So we're doing question 22. All right. So a student in her lab measures the standing wave modes in a tube. The lowest frequency that makes a resonance is 20 hertz. So that means it's going to be F1. This is ridiculous. F1 is 22 hertz, or excuse me, is 20 hertz. Jeez. As the frequency is increased, the next resonance is at 60 hertz. F, the next one. And this is do we know it's a tube?
no, you're supposed to figure it out.
Okay. So it's 3 times as much, isn't it? Which means that this is F3. It means that it must be a tube closed at one end and opened at the other end. So that means that we've got F sub n is equal to n times V over 4L. Is that okay with everybody, what I'm writing down there? Number 1, did I do it right? Number 2, does that make sense to you? I guess those are 2 questions I want to make sure. So the rule is that if you've got a string or you've got an air column open at both ends, then it's Fn is equal to n times V over 2L.
Both ends open.
Both ends open. So flutes and stringed instruments is 2L.
Yeah.
Saxophone is this. So if you watch the video, you know that you've got the string instruments, you've got the percussion that we don't really care about, no offense, and you've got 2 different kinds of air columns. You've got the flutes and you've got everything else. Okay? Like flutes and piccolos and whatever, like that's all the same thing. And then everybody else. Everybody else follows this. And everybody else follows that where n must be odd.
So that's how you know that.
That's how you know that, because the first one is 20 and the next one is 60. That's 3 times. It's not just a 2. So that's the hint that tells you that much. Okay, and then it says, as the frequency is increased, the next resonance is, okay, what will be the next resonance? So that means that we need to know that it's F5, right? And so then we're going to multiply this thing times 5, right? So that's going to be 100. Elizabeth, does that make sense to you?
Yeah.
Okay. Did you want me to go through another one, or are you feeling okay?
I think I did okay.
Okay, let me know if you want more. Henry, what's up?
Do you have like a graph problem where you like snapshot there's over a long time graph?
I don't know what you're talking about. Tell me more.
The history graphs.
Yeah, the snapshot history graphs.
Those are.
Yeah.
Yeah, those
Yeah.
are confusing too. Snapshot and history graph.
I don't like
Yeah,
it.
for the test.
It's probably-
Otherwise, I'm not going to worry.
I don't know what you're talking about. Maybe I'm feeling really dumb.
Like the very beginning homework.
Chapter 15, problem 22.
That's what I want to know. Thank you. Chapter 15, what'd you say? Problem?
Yeah.
Problem 22. Let's look. Thank you. That helps me more than like, because I just, yeah. Oh, yeah. I know what you're talking about now. Sure.
Oh, she got excited.
No, I mean, no. I'm just saying, I understand. I didn't know what terminology meant. So I'm doing, right. Oh, hi. Go away. I don't want a quick note. I just want to do my work here. Come on. Chapter 15, problem 22. That's what you said, right, Ellie? Okay. So I'm going to throw this up on the board. look at that. It was like almost perfect. I shouldn't have moved it. All right, there it goes. Brilliant. Okay, here we go. So, ooh, that's gross now. Focus. There we go. All right. Figure P1522 shows a snapshot on the left and a history on the right for a wave traveling on a string. The snapshot graph shows the wave at t equals 0. The history graph shows the displacement of the point on the string. Okay? Hold on. What is the speed of the wave and in which direction is it traveling? Okay. So what do you do? How did you look at this?
I don't.
Get us started, Jasmine.
So the snapshot graph.
Guys, listen up.
Well, the snapshot graph shows like 1 point at 1 moment in time.
Uh-huh.
So and the history one shows that point's motion over however much time is on there. So the history graph shows that the point goes up and then down. So if you look at the snapshot of the wave, it would look like the wave would have to travel to the left in order for that turn to go up. So we know that it was traveling to
Hold
the
on, just dup. I'm gonna let you know. I've been teaching physics a long time, and I don't mean this in a critical way, but I mean it in a if you have an open mind about trying to learn something, even if the first description doesn't make sense, it makes it a lot easier to try and learn it as opposed to nope, I don't get it. Okay, so let me see if I can use your words again. Okay, so you remember when we had the mass on a spring, right? Bouncy, 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 and we basically built this graph. So this is the mass on the spring. At time equals 0, it was at equilibrium, okay? And then at time equals 1 or 5 milliseconds, it goes up, and then it comes back. So this is like the bouncy, bouncy graph from the simple harmonic motion, okay? And as this wave is passing through this point, that wave is this point is just moving up and down and up and down. It's a transverse wave, which means that this point is not going anywhere left and right. It's only oscillating up and down, up and down, up and down, just like a mass on a spring. Okay? So far, so good? So what Jasmine said, I think, so correct me if I'm wrong with what you're saying, is that it starts at 0, right? And then it moved up. So it moved in the positive direction, and then it moved in the negative direction. So if it moved in the positive direction or moves in the positive direction, that means that this wave, you're saying, had to have come from the left in order for it to move in that direction. Okay? Ish. Let me say one thing real quick, Nick, and then I will address it. There is not a question exactly like this on the test. Okay? Does that make sense? That said, this concept of being able to interpret what a point is doing as a wave travels through is something you need to know. Okay? Go, Nick.
I was just going to say that speed of the wave is the wavelength times frequency, the wavelength over period, and you can find the wavelength on the left graph and the period on the right.
That's clever. Did you catch what he said? Do you want me to repeat that, or did that make sense to you guys? Repeat it? Okay. Keep talking. Say it again. So from this graph here, you can find the wavelength, right, from crest to crest. So the wavelength it looks like is 2 centimeters. And then you're saying from this one, because you've got distance and you've got time, you can find the frequency or the period. Do you have a preference? Yeah, you can use period, sure. So how long does it take for it to get from here to here? Hey, it's like they did it on purpose that way, right? So the period is 15 milliseconds. Okay, is that making sense? So then you've got wavelength and you've got period, so you can find the speed. Yeah, that's clever. It's kind of like with the stuff that we were doing before, where you can find so much stuff out by just a simple little picture. You just have to be able to dig. You have to be able to dig.
I
Go.
still understand that you find out which direction it's traveling.
Yeah. Because because like